Okay, this is going to be the lecture over Chapter 15, Oscillations in Physics 1. We're going to be discussing simple harmonic motion, and we'll distinguish simple harmonic motion from other types of periodic motion. And we'll take a look at some equations here to describe not only the position, but also how that position changes over time. So we've got a number of objectives here to cover. All right. So the frequency of an oscillation is going to be the number of times per second that it completes a full oscillation or a full cycle. So the unit of hertz is going to be defined such that 1 hertz is 1 oscillation per second. The time in seconds for 1 full cycle is going to be the period. So if you take the frequency, take its reciprocal, then you're going to end up with the period. And that's how they're related to each other. Any motion that repeats regularly is considered to be periodic. Simple harmonic motion is a periodic motion that is a sinusoidal function of time. So the x, the position as a function of t, is going to be x maximum displacement times the cosine of omega t plus phi. So this function right here is going to oscillate between -1 and 1. And when multiplied by the maximum, it will give us where that particular motion ends up in between the extremes. So we've got a particle that is oscillating in this diagram left and right. So we start here, then it oscillates back this way, then it oscillates back this way. So as the time passes up to the full period here, we can see that it makes the motion out to minus the x maximum and then to plus the x maximum. We can see here at t divided by 4 and 3t divided by 4 that it ends up back at a position of 0, and that at half the period it ends up at the negative, the x maximum. So the speed is 0 at the extreme point. You can see here there's no velocity, and no velocity. You can see the velocity increase as it swings out this way, and then you can see the velocity increase as it swings out the other direction. So if you take that particular motion and rotate it 90 degrees, you can see that the figure is going to be the motion of a cosine function. And what that means is that if you start here and then go down and then go up, so basically take this, turn it 90 degrees counterclockwise, this is the kind of motion you get. So this is the graph of the motion with a period indicated. The speed is 0 at the extreme points, and then the speed is greatest here because all of its energy is going to be kinetic. All right. So the value written x sub m is how far the particle moves in either direction. That's going to be called the amplitude. The argument of the cosine is going to be called the phase. The constant phi is going to be called the phase angle or the phase constant. It's basically what allows you to be able to calibrate where you are in the motion. So you may not always start out the motion at a particular x sub m. It may be somewhere different, and this phase angle helps to compensate for or helps you to know where that's going to be. And as it says here, it'll adjust for the initial conditions of motion at t is equal to 0. The angular frequency is going to be written as omega. So the displacement at time t is going to be equal to the amplitude times the cosine of the phase, and the phase is broken down to angular frequency times the time plus the phase or phase constant to make sure that you're at the position in the cycle where you want to be. So angular frequency has a value of 2 pi divided by t. And if you'll remember, the frequency was 1 over t. So if you multiply both sides by 2 pi, this is how you can relate all of those particular values. So you can see here that the amplitudes are different, but the frequency in the period is the same. In other words, this is going to go further up this way, and it's going to go further down this way. But it's going to cross the t is equal to 0 at the same points. And it's also going to reach its maximum and minimum at the same points. And here you can see that the amplitudes are the same. In other words, the swing in and out is going to be the same, but the periods and frequencies are different. And you can see here, if the phase is going to be 0, that this is where we're going to start out. But if the phase is minus pi over 4, it's going to move this particular graph out. So particle undergoing simple harmonic oscillation of period t, like that in figure 15.2, is at minus x sub m at time t is equal to 0. Is it at minus x sub m at x sub m or at 0 between minus x sub m and 0, or between 0 and minus x sub m and positive x sub n? When a is the time is equal to twice the period, when time is equal to 3.5 times the period, and when the time is equal to 5.25 times the period. So if it starts out at minus x sub m at time is equal to 0, then if you go out twice the period, you're still going to be at that same particular spot. Reason being, let's see if we can find a good solid. Yeah, let's try this. If you take this and you want to find out where it is, not at 1 times the period, but twice times the period, it's still going to have the same shape. So it's still going to be at, well, in our case, at minus x sub m. At 3.5 times the period, basically, if you were to go out 3 times the period, you'd end up with the exact same answer as what you've got here. But when you finish half the period more, you're going to be at the opposite end of the oscillation. So it's going to be at x sub m. And then if you're going to take it and multiply it by 5.25, you're going to be 5 times the period. That would put you back at x minus x sub m. But if you go just a quarter of the way further, it will put you right in between those two values and will put you at 0. So if you take the derivative of that particular function, you're going to find the velocity, and the velocity is going to be equal to minus omega x sub m, the angular frequency times the amplitude times the sine of omega t plus phi. And the value omega x sub m is going to be the velocity amplitude, or v sub m. This is going to be the maximum value plus or minus that it's going to be away from 0. The acceleration can be found by taking the time derivative of the velocity function, or the second derivative of the position. So the acceleration is going to end up being minus omega squared x sub m times cosine of omega, and there should be a t there, but there isn't, plus phi. this value is going to be called the acceleration amplitude. So you can see the position amplitude was x sub m, the velocity amplitude was omega times x sub n, and the acceleration amplitude is going to be omega squared times x sub m. And it all comes from taking the derivative of a trigonometric function where you're also taking the derivative of the argument inside, and that gets put out in the front. So how is acceleration related to position? Well, if you go back, let's take a look here. X sub t is equal to x sub m times cosine of omega t plus phi. We're looking at this, x sub m times cosine of omega, which should be a t, plus phi. This gets defined as x sub t, but we have this other term out there in the front. That's how those two terms are related to each other. So here's a graph of the displacement of the velocity and the acceleration. So if you have the extreme values at 0 times t and then 1 times t, those extreme values mean that our velocity is going to be 0. So in other words, our velocity graph should be crossing the t-axis here at 0 at those extreme values, and indeed they do. And then if you go back and you take the derivative of this function, you're looking at the slope of that, you're ending up with extreme values here just on the opposite side, minus omega squared t. So that should follow from the definition of the formulas there. So in simple harmonic motion, SHM, the acceleration is proportional to the displacement x, but opposite in sign, and the two quantities are related by the square of the angular frequency. So check point 2. Which of the following relationships between a particle's acceleration and its position indicates simple harmonic motion? So for simple harmonic motion, what is the angular frequency? So the relationship is going to end up being C, where the angular frequency is 2, because 2 squared is going to give you 4. So if we apply Newton's second law, force is equal to mass times acceleration. We know what acceleration is defined to be. And then we leave the x by itself. We pull that omega squared in here with the m, keep the negative out there. We're relating this to Hooke's law. We can see the similarity. So simple harmonic motion is the motion of a particle where the force acting on it is proportional to the particle's displacement, but in the opposite direction. And if you remember, Hooke's law, F is equal to minus kx. We can call this k. The important thing here is that it's proportional to the first power of x and that there's a minus sign out there. So linear simple harmonic oscillation. Force is proportional to x to the first power is going to give you the angular frequency, where omega is going to be equal to the square root of k divided by m. And the period is going to be 2 pi times the inverse of this, so the square root of m divided by k. That's going to be your period. All right, so checkpoint number 3. So which of the following relationships between the force on a particle and a particle's position gives simple harmonic motion? Well, A is the only answer because it has to be proportional to the first power of x. But in this case, the force is equal to positive a number times x. And what we need is a negative number times x. That's what defines it as simple harmonic motion. So inevitably, we're going to come around to trying to define what kinetic and potential energy is going to be for situations with simple harmonic motion. So write the functions for kinetic and potential energy. For our potential energy there, we've got 1/2 kx squared, or 1/2 k x sub m squared times the cosine squared of omega t plus phi. Kinetic energy is going to be 1/2 mv squared. And again, if you just replace the values there that we derived earlier, then we arrive at their sum, which is going to be defined as the potential plus the kinetic, or 1/2 big K x of m squared. There takes some trigonometric stuff in order to be able to compute that, but that can be done. Here's the trade-off for both potential and kinetic energy. This graph is going to represent zero energy down here, and it's divided out in the time periods here on the t-axis. And the entire energy of the system is going to be defined with this black line. It's going to be constant. So we're not losing energy at any point. As we first start this out, our potential energy here in green is going to start here, and it's going to decrease. As it decreases, the kinetic energy of that object begins to increase. And these two continue to trade off time and again. As time changes, the energy shifts between the two types, but the total is going to remain constant. So in this figure, the block has a kinetic energy of 3 joules, and the spring has an elastic potential energy of 2 joules when the block is at x is equal to 2 cm. So what is the kinetic energy when the block is at 0? When the block is at 0, all of the energy is going to be kinetic. So whatever potential energy was there is going to be added to the kinetic energy, and so you're going to have 5 joules at x is equal to 0. What is the elastic potential energy when the block is at x is equal to minus 2 cm? That's going to end up being 2 joules. And then when x is equal to minus x of m, pardon me. The elastic potential energy when the block is at x is equal to minus x of m, you're going to have 5 joules of energy, because when it gets to the maximum, it's no longer moving. And when it's not moving, it doesn't have any kinetic energy anymore. It's all potential. So, torsion pendulum. The elasticity from a twisting wire. So it moves in angular, simple harmonic motion. So we have an angular component here to the linear. And so the torsion constant is going to be K. So tau is going to be equal to minus, I think that's kappa, times omega. Theta, I'm sorry. And this is the angular form of Hooke's law, and replace the linear variables with their angular analogs. So in other words, if the force was equal to minus k x, then the torque here is going to be equal to minus kappa times theta. We find in this particular case that the period is going to be equal to 2 pi times the square root of the moment of inertia divided by kappa. So we've got our fixed in here, we've got our suspension wire, we've got our reference line, and this sucker is sort of turning this way and that. It turns from minus theta sub m to 0 to theta sub m, which actually should have gone that way. And so that's how the wire is rotating in a pendulous fashion. So a simple pendulum. A bob of mass m suspended from an unstretchable massless string. So the bob feels a restoring torque, in other words, something that's going to pull it back to where it was. That torque is going to be equal to minus the angular momentum times the force of gravity times the sine of theta. If you relate that to the moment of inertia, then you find out that alpha, or the angular acceleration, is going to be equal to mgl divided by the moment of inertia times theta. So if you go through and you make the replacement here for this and solve, you can come up with theta. So we got our pivot point here, we've got a length L, we've got a mass M. So you've got gravity, which is acting on this particular bob. You've got theta, which is going to be S divided by L. That's going to be the arc length that's traced out. You've got the tension acting here. You've got theta, the angle that's created. You've got the mass M. And then you've got the force of gravity is pointing down. So if we figure out the orthogonal components here and here, this component right here is what's going to try to bring it back to the center. This just pulls on the string. So the angular amplitude, theta sub m, of the motion must be small. In other words, when it starts getting larger, we end up having problems with simplification of terms in math. The angular frequency is going to be equal to the square root of mgl divided by I. And so the period for the simple pendulum, where the moment of inertia is equal to ml squared, ends up becoming this. And now a real physical pendulum can have a complicated mass distribution. So if we look at this as this is the fixed point and this is the center of mass, we can again try to model what's going on here by using this particular center of mass and watching its motion. So an analysis is the same, except that the length, L, we have distance h to the center of mass, which, there we go. So this length L, which normally on the bob would go all the way down, all the way down to mass M, which is probably considered to be small enough to almost act like a center of mass. In this particular case, it's replaced with a length h, which goes down to the center of mass. And so the moment of inertia will be particular to the mass distribution. So the period becomes this, and a physical pendulum will not show simple harmonic motion if pivoted about its center of mass. The center of oscillation of a physical pendulum is the length L naught of a simple pendulum with the same period. And a physical pendulum can be used to determine free fall acceleration g. So assuming the pendulum is a uniform rod of length L, then we go through and compute its center of mass. If we solve this for g, we come up with g is equal to 8 pi squared L over 3 times the square of the period. So let's say that we have 3 physical pendulums of mass m naught, 2 times m naught, and 3 times m naught, and they have the same shape and size and are suspended at the same point. Rank the masses according to the periods of the pendulums, with the greatest first. This is a trick question. Because if you go through here, you find out this is related to G, it's related to L. It never really gets related to mass. Mass does not affect the period of the pendulum. That's what this is trying to reflect. So simple harmonic motion is circular motion viewed edge on. Simple harmonic motion is the projection of uniform circular motion on a diameter of a circle in which the circular motion occurs. And we'll take a look here at the figure that shows a reference particle moving in uniform circular motion. And the angular position at any time is omega t plus theta. So we've got P, which is a projection moving in simple harmonic motion. And this is a particle that's moving in a circle. You can see all of the component parts here. This is the maximum displacement that occurs. This is the displacement that actually happens, and this is the angle that's formed at a particular time. We can see the velocity vector, both this direction as well as this direction. And then we can see the acceleration at each of those points as well. So if we project its position onto X, this is the formula that we can use for it. Same thing goes for velocity, and the same thing goes for acceleration. And we find that this projection is also simple harmonic motion. Now, when an external force reduces the motion of an oscillator, it is considered to be damped. Assume the liquid here exerts a damping force on this motion. And that damping force is going to be proportional to the velocity. And this can be shown to be accurate for slow motion. This B is going to be the damping constant, and it depends on the vane and the viscosity of the fluid. So we've got the springedness, we've got the mass, and we've got the vane, and we've got the damping. Using Newton's second law, and we can rearrange this, we can find that the solution to this differential equation is going to be x of t is equal to x of m times this constant times the cosine of omega prime t plus phi. This is also going to have this particular angular frequency. I'm not going to go through the derivations on all of this, but this is the information that you do need to know. So if you look at damped simple harmonic motion, rather than having a sinusoid motion that continues on at this, we see that the maximum in the displacement on either side begins to get less and less and less, and it's because of this exponential term. If the dampening constant is small, then we can just say that omega prime is close to omega. And for small damping, we find the mechanical energy by substituting our new decreased amplitude, where the mechanical energy is equal to 1/2 k x of m squared times e to the minus bt divided by m. So here are 3 sets of values for the spring constant, damping constant, and the mass for the damped accelerator in 15.6. 1516. Rank the sets according to the time required for the mechanical energy to decrease to 1/4 of its initial value, greatest first. So if we take a look here, which one of these is going to have it decrease to 1/4 of its initial value? Well, a lot of that is going to end up being dictated by B and M. And if we look at this, if B and M gets greater and greater and greater, then the dampening effect of that term is going to be bigger much more quickly. As that term as you can see, as the ratio of those two terms begin to increase, then this particular value tends to increase quickly. And if you put that term in the denominator, you can see how that begins to decrease that particular value. So this is going to decrease a lot less quickly than this will, because if you look at the ratio of this to this, it's less than this to this, which is less than this to this, which means this time, it's not going to be anywhere near as long as what it would be for this as what it would be for this. That's why it's ranked 1, 2, and 3. So forced or driven oscillations are subject to a periodic applied force. A forced oscillator is going to oscillate at the angular frequency of its driving force. The displacement amplitude is a complicated function of omega and omega naught. The velocity amplitude is greatest when omega sub d is equal to omega. And that condition is called resonance. It is also approximately when the displacement amplitude is the largest. So the resonance has important implications for the stability of structures. Forced oscillations at resonant frequency may result in rupture or collapse. If you've ever seen the image of the bridge out in, I guess it was the Pacific Northwest, that ended up collapsing because the wind started hitting the bridge and causing it to resonate. That's a really good example of this. Okay, so now we have the summary of all of this. Again, these notes will be made available to you to look over. And I hope you got something out of the lecture.